Hello. Yeah. Well, it's a great pleasure to have here Patrick Brady, the spokesperson of the LIGO Scientific Collaboration. He came here to discuss with Giovanni and a little bit also with me. It was a great pleasure to exchange. It is always the occasion. We asked him to make a presentation and he gladly accepted, and that's a big honor for us, a big pleasure too. And what else? I mean, it's also, these talks is the occasion to see the CV of people you know and you know, admire since a long time. You know, I mean, personally admire, as I say, for both for him and Giovanni, the way that they coordinate huge collaborations with a lot of people, and that demands special skills, and I think they both have them. Permit me to put Giovanni together with Patrick, and then of course the other part of his CV is that he is a professor at the University of Wisconsin, Milwaukee. He has had many prizes along his life. It would be too long to list the prizes he has received. I was impressed by the quantity of students which supervise the PhDs you have done in your career and continue to have, actually, in parallel with the other tasks. And of course, many other collaborations, programs by NSF and other organizations. And so it shows a brilliant career. So having said that, and I don't want to take more of your time, I would like to introduce Patrick. And okay, and stay connected immediately afterwards. Probably we'll show it directly from ESA, the announcement of the ESA, the Event Horizon news at 3 o'clock. So it will be an exciting evening. So cheers.
Stavros, thank you very much for the introduction. I hope I'm okay online in terms of being heard. So it's very nice to be here. This is one of my first research visits with Virgo colleagues since Warsaw in 2019. So it's more than 2.5 years since we've been able to sit in person and do something. One thing about the presentation, this was a recycled presentation. It was given a few weeks ago at a theoretical physics workshop where they wanted an overview. So a lot of it will be stuff you know, and I'll touch on a few things perhaps that you're interested in learning something else about or asking about. And last but not least, I will try to stay on time so that we can actually get to ESA in a timely way. All right, so as I said, for this audience, the intro is very basic, but I've started including this talk here, or this present slide here, for 2 reasons. First is that we're beginning to discuss the International Gravitational-wave Observatory Network as an organization, and so it's nice to begin telling people that we exist as such. And the second thing is that we probably all are aware, we're trying to make sure that people, when they discuss gravitational wave detections, refer to LIGO, Virgo, CAGRA, and not just one at a time. So this is a new push. So I really just want to emphasize that here as well as in other talks. So the material that I intend to cover today is I'm going to give you some highlights that I sort of like to look back on for the last 7 years, discuss a little bit about the sensitivities, what we've found, what a large number of firsts, it's rather amazing, talk about compact binary mergers, and then discuss a little bit about the other searches that we do, looking for other sources. You'll hear later on in the talk then, as I move on, to discuss the period from now through to 2025, and then from 25 to 30, and eventually into the next generation facilities. For me, I'm excited to think about what discovery space we may open next. And that for me is just really interesting to look for as we watch the sensitivities improve. So this is a reminder of how we've done so far, starting back in 2000 and, let me just adjust things here. Starting back in 2015, the LIGO detectors were ready to undertake their first observing run. Virgo was a little bit behind. We were chatting last night about how the 2-year gap showed up due to various let's say, aspects of getting the site originally. So these things in these big projects trace back a long way. But LIGO turned on in 2015, and everyone knows the story. Turned on the detector, started to take engineering data, and before the observing run was officially supposed to begin, we already found the first detection, so GW 150914. You can see as the years go by and observing run 2, observing run 3, the sensitivities as they change. Which I realized, do I have a pointer that I can use here, or is it better? Let me, oh, it's okay. I'll use the arrow on screen. It's that way people on screen can see it too. So as we can see, if we take a look at the sensitivities on the right-hand side here, the horizontal axis corresponds to our binary neutron star range, and the vertical axes for each of the runs, 01, 02, and 03, are histograms of those ranges taken at intervals repeatedly during the run. And so we see that initially in 01, the Livingston and Hanford detectors had sensitivities that were somewhere around this 80 megaparsecs range. But then in 02, we begin to see some improvements in sensitivity at Livingston. Hanford actually fell back a little bit, and we got Virgo to join the network. And then in 03, we see that we continue to see improvements in the LIGO and Virgo detectors. And in particular, the histograms, the height of them represent how much time was accumulated. And so we see from 02 to 03 that Virgo became an equal observing time contributor to the network at that time. The other milestones to be aware of here, and we'll touch on them again in the next few slides, of course, is GW 170817. At least, at the beginning of this, I had concluded that every time you turn on a new detector, you're going to get a new dramatic discovery. That just was my conclusion post GW 170817. It came within days of Virgo turning on to join 02, and we'll mention a little bit about the exciting science. But then one of the big milestones to be aware of is this other transition that occurs in 2019. When we went into 03, we went from having proprietary alert data about gravitational wave discoveries to a time when we actually tell the world about these things as soon as we know. And you'll see a little more about the timeframes of that as we go. A little more about the sensitivities and the detections. I really like the plot on the right here. It just begins to show you just how the rate of detections increases so dramatically as you increase the sensitivity. You have 01 and 02 with detection rates that are actually fairly similar per unit data taken. But when you get into 03, the increase in sensitivity for the most sensitive detectors increases the rate of discovery dramatically. And you see it through this slope that has changed and increased over here on the right. So in 03, we had one detection every 5 days on average. Again, huge change compared to no detections before 2015. And the promise of the future is even more dramatic than that. So then let's take a look, though, with all of those detections that we've made, what were they, and what new science were we able to do with them as they came along. So 150914, well, we all know that one. It's the one that is the first discovery of a gravitational wave. So it's dramatic in that regard. For me, it was extremely dramatic in the sense that when you looked at the wave and tried to explain it, you concluded it had to be a pair of black holes colliding. And I remember, in fact, about 3 days after the gravitational wave passed by, and we were all quite excited, as everyone remembers, I was actually walking out the door of my house, and there's a little hill up into a park, and I was smiling as I was heading for the office. And it was the early part of the teaching semester, so I'm not always smiling on those days and those mornings, but I was, and I noted it, and I just sort of said to myself, it's like, holy, that's amazing. We detected a gravitational wave from a pair of black holes that were 1 billion light years away. And so this was a very dramatic discovery and brought already two aspects, right? The measurement of the gravitational waves and this more direct observation of black holes. 170817, then we have the first detection of binary neutron star mergers. And on the right, on the graph here, what you see is the horizontal axis corresponds to one of the elements of the binary. So in solar masses going from 1, 10 up to 100. And on the vertical axis is the secondary mass of the binary going from 1, 10 up to 100. And each of the dots represented on this graph represent a binary merger of some kind that we've actually been able to measure the gravitational waves from. So 170817 was the first one that's way down in this corner down here. And it was our discovery of binary neutron star mergers. We knew binary neutron stars existed through pulsar observations for many years, but to see them collide was tremendous. And of course, we got that dramatic association with gamma ray bursts and then all the additional science that came with it. So that was the second very dramatic discovery. One of the next first that I like to note is 190521. This one is a particularly massive binary. You see it sitting on the right up here, close to 100 solar masses on at least on these graphs for both of the elements. And so this is thought to have a pair of black holes that have masses that are in a region which is not very well understood in terms of the astrophysics and the stellar evolution that leads to the formation of those black holes. So actually getting one of those, getting a pair and being able to measure them was a dramatic discovery for astrophysics. And so this, the region up there is known as the pair instability supernova mass gap. And it is, the idea basically is that when you actually get a supernova trying to happen in a very, very massive star, it actually becomes even more powerful than a standard supernova once the star gets to a certain size. And so it can actually disrupt the situation completely and not leave behind, in fact, any compact object. That was the sort of idea. But seeing something up there, maybe that stellar evolution and that understanding is not quite correct. And then the other one that I like is 190814. This one was something that started to show us also the collision of binaries, whereby at least one of the objects is between 2 solar masses and 5 solar masses. And that's important to us because we have known about neutron stars where we could measure their masses up to around 2 solar masses, but not above. And for black holes that were observed electromagnetically in the galaxy, there appeared to be a lower bound of about 5 solar masses. So we hadn't seen any compact objects through electromagnetic observations in that gap between 2 and 5. And so now to have a binary where we say, well, there's a high likelihood that one of the elements of this binary has an object in that gap, starts to then bring up the questions of how did it form? Was it hierarchical through collisions of 2 smaller objects? Do we actually see just primary formation in the gap or not? And so those are nice new questions that arise as we go forward. Now, I also, in terms of me, as I think about these things, I go over the few things that I really enjoyed as we made the discoveries. And one of my favorites is the speed of gravity constraint that we were able to do with GW 170817 and GRB 170817A. That is a really tremendous result. It involves only really 2 pieces of a measurement. The first one is the time delay between the merger, which on this diagram, the time is indicated on the horizontal axis, and then this time frequency plot down the bottom represents the gravitational wave signal coming in here and sweeping upwards in frequency. And then each of these three panels represent gamma rays that are measured by different satellites. And what you see is that the merger time indicated along here by this vertical axis, and the time when the gamma ray astronomers say the gamma ray burst happened, which is indicated by this light gray line here, is about 1.7 seconds apart. And when you take that measurement, just literally the time delay between those two things, and then you fold it in with our ability to measure the amplitude of the gravitational wave signal, and by that measure the distance to the source, you get this tremendous constraint on the speed of gravitational waves. It potentially goes backwards, but from -3 × 10 to the -15 up to 7 × 10 to the -16. So this is, in fact, a really dramatic result. It improved the measurements of the speed of gravity by I can't remember the exact number, but I think it's 10 to the 12 or something overnight, essentially. And so it's just amazing how much was known right away. Of course, there was also the discovery of the optical transient AT 2017 GFO, and that brought with it a wealth of knowledge about the kilonova explosions that are associated with the merger of neutron stars, what types of elements are formed in them, and essentially hinted, and you know, I would say it's strong primary evidence that these are the sources of the lanthanides, the heavy elements that were not fully understood about their origin before that. It had been hypothesized back actually in the 70s that there might be an association with neutron star mergers as sites for the generation of these elements, but this was the first real primary evidence for it. And of course, it just keeps going. That's the wonderful thing about the last few years, right? We had another first not too long ago where we published this paper about several neutron star black hole mergers. You see on this graph, again, the primary masses along the horizontal, up to about 25 solar masses. The secondary is along the vertical from 1 to about 2.75 solar masses. Each of these shaded regions represent the posterior probability distribution over the masses for one of the gravitational wave events listed here. The pair GW 200105 and 200115 are the ones that we focused our attention in this paper on. And when you look at them, you see just quite nicely, you see that the 05 one, which is this sort of orangey one here, has a sort of a mode which is around a primary around 10 solar masses and the secondary somewhere just around 2 solar masses. So this is consistent with what we know to be the masses for neutron stars and for black holes. So it's a beautiful discovery in that regard. If you go to 200115, you find that here we end up with this lower mass primary. It's around 7 solar masses at the mode. And the mass then has a tail that also dribbles up into above 2 solar masses. But it is still very, very clearly something that looks like it is a neutron star with something around 1.4 solar masses and a black hole somewhere around 7. Now, that again, just lovely discovery. No electromagnetic counterparts to those objects, but maybe in the future runs we'll see that. And then the classic summary that was generated by Aaron Geller from Northwestern that now has the summary of what we've been able to do with gravitational wave observations of binaries. And it's just amazing. A few years ago, one used to say, oh, this will fill in rather quickly as we get more sensitive. And now you have to remind people to peek and look quite carefully for these sort of reddish colored dots on the right and the left, which represent the masses of the black holes that were identified electromagnetically before well, actually, were identified electromagnetically, and that represented pretty much everything we knew about black hole masses before 2015. And now you've got this whole set of things going on where we get to measure the primaries, which can be compared directly to those red dot masses. And then you can also look at the secondaries to actually start to think about how you accumulate more massive black holes through collisions. And so this is actually just wonderful to see it coming into its full self. So I'm not going to say much about populations. This tends to be a fairly big focus of the science we talk about and hear about from at least a set of the observers that emphasize this particular piece of work. It's great initially, the first couple of detections, we had one number we wanted. It was the number of events per year per gigaparsec cubed, right? That was it. And we were thrilled to be able to measure it. But now, with nearly 100 gravitational wave observations in the can, most of them being binary black holes, we can actually get to ask questions about the mass spectrum of those objects. And so this diagram is from our paper that's on the archive. Actually, I think it's published by now, but our paper that's talked about here on the archive. On the horizontal axis, you have the primary mass going along there. And on the vertical axis, you have the rate density. So you just think when you look at this, if you've got a high point here, then objects that are in this mass range are more common than a low point down this end where they're more rare. And what we begin to see in this is structure. Well, if you squint, maybe you're willing to identify structure. It depends, and it depends on exactly what analysis you do. It looks like, you might draw out a peak somewhere in here around 30 solar masses on one of the objects, and a peak down here sort of close to around 10 solar masses. One of the great things about the next run will be trying to figure out whether or not they survive the test of time. As we know, peaks can come and go quite often in distributions. So I want to switch gears now for a minute, because I do want to emphasize something that I think is going to be more and more important as the signal to noise ratios of the events we detect go up. And that is that with these observations, because the systems tend to be quite clean, there's not a lot of astrophysics going on in the phase while you get the two objects spiraling together and then eventually crashing into each other. Right at that end, if they're neutron stars, sure, there's a whole host of astrophysics, detailed physics that has to be calculated. But while the objects are further apart and they're slowly, relatively speaking, spiraling into each other, then there's not much that affects the dynamics except for gravitational wave emission. And so as a result, when you measure the gravitational waves, you can begin to ask very detailed questions about the accuracy or validity of general relativity. And so this example here shows you, first of all, the type of phase as a function of frequency that we expect to see from a gravitational wave due to a colliding black hole. It's represented in the post-Newtonian calculational framework, and you see various terms, including this sum here, which shows that you're summing up terms in that post-Newtonian representation. What we do in the collaboration then is we start out with the calculation done in general relativity with the coefficients that we actually can calculate exactly that plug into each of the parts of this equation. And then we say, well, let's imagine that those coefficients are slightly wrong and ask the data to tell us what they should be. And so we then go along and we ask the data to tell us and we do it in terms of deviations from the general relativity value. So the deviations from the general relativity value are shown on the vertical here. The horizontal is a probability. And so you look at these things that we call the Violin plots, and when they're peaked, it means that the most likely value is at that value. When they've got tails, they're not. And so you see, for example, if, well, let me not pick the minus, let me pick the 0pn case first. So the 0pn case down here, phi 0, you see that the peak is very, very close to 0. You see the distribution, the bulk of the distribution contains 0 very, very well, certainly within the 90% contours. And so as a result, we don't see any deviation in the phi 0 coefficient. And then you do that going along for each of the coefficients, trying to find out whether or not we can measure any deviation. It's perhaps not the best test that you could invent, but it's the one we can do today, and it works, and it's been shown to work quite well. The question I think that we face as gravitational wave astronomers going forward is, as we make more observations to this, how would we know for sure that we'd actually measured a deviation? Now, I mentioned already the systems are clean, so that tends to take a lot of systematics related to astrophysics out of it. But there is the statistical problem. We keep measuring. At some point, you're going to see things that actually deviate. And so you need to make sure you control and understand the statistics of this measurement. So that, I think, is going to be a challenge for us going forward. Another measurement that we've been able to do is to test modified dispersion. This idea originated from Cliff Will back in the 90s. He basically said if there's a mass associated with the graviton, it's going to lead to a dispersion of the gravitational waves as a function of frequency. Since the binary signal sweeps across the frequency band, you can actually measure a deviation, a dispersion of those waves that's different than is expected from the binary itself. And so we've been able to place a bound on the A0 number that would appear here in this dispersion, modified dispersion relation, where if this is equal to 0, then this is just the zero mass and the standard dispersion relation for gravitational waves. This plot actually shows the details of it, but let me skip over that because I want to move on to other things. One test that I like very much, and I think it's early days for it, but it's going to be something that we can do more and more as we move forward, and I think we should pay attention to a lot more, especially with the network, is the polarization tests. These are very basic fundamental tests because when you take a look at any scalar tensor theory of gravity, you can actually list out all of the polarizations that are possible in gravitational waves. And they're shown on the right here. There are 6 of them. Cliff Will documented them in his paper or in his book and also in the Living Reviews, and it originates back in the 70s. And so as we add more detectors that are not co-located and co-aligned, we begin to be able to disentangle the different polarizations. And so as we bring up the network with more and more sensitive detectors, we're going to be able to do a better job at this type of test. And so this is one of the beauties of as Virgo has come into the mix with increased sensitivity, it's been great because we now have 3 detectors we can start to disentangle. If we can get Cogra into the mix with adequate sensitivity, we'll begin to get at another level. And then if we can actually add LIGO India, yet again, another improvement. And so this is the nice thing about this test is it's very clean and general. It doesn't rely on modified waveforms too much. It really depends on just knowing how the detectors respond to the different polarization states. Okay. So the last just nugget of science that I'll mention today is cosmology. I like this one as well. I found it to be very compelling. Again, GW 170817 is at the center of our first measurement of that. Once we had the optical counterpart, AT 2017 GFO, and we knew it was in NGC 4993, we were able to get a redshift from the optical counterpart measurement. We were able to measure the distance again from the gravitational wave measurement. And we all know you take the ratio and you get the Hubble constant. And to be honest, I think within hours, pretty much everyone had done this calculation to just check whether or not we actually kind of were getting something roughly correct. But the analysis that was reported based on a proper Bayesian and more careful Bayesian analysis is shown here. And we, of course, split the difference between that tense relationship between the supernova group and Planck on what is the Hubble constant, and we just went right in the middle. Since then, we've been able to take some of the data from 03, and by taking a look primarily these days for features in the gravitational wave mass spectrum, we can place slightly tighter constraints on the Hubble constant than we were able to do in previous runs. And so those results, which are reported in this paper here, are shown here on the right. And you can see that the width of the posterior is beginning to close in a little bit, but we still have a long way to go. And the more counterparts we can add, the better that result is going to be. So sky localization and counterpart identification are going to be a key part of this. We should continue doing the mass spectrum evaluation version, and we should add in just galaxy catalog blind evaluations as well. But again, you just can't do much better than the electromagnetic counterpart. So with that overview, let me now switch gears to where we're going next. And I know everyone here is well focused on this. So this is our run plan with you know, an overview where I think the 04 plan feels pretty solid at this stage. You know, it might slip a little, but we all feel pretty good that that's coming about. So it's going to be about a year. There'll be a little bit of commissioning breaks in and out between. We're going to have LIGO and Virgo coming on as a network together with CAGRA. Sensitivities for LIGO are going to be somewhere in the range, hopefully from 160 to 190. Still an open question, no measurements yet to guarantee that, but we're hoping. Virgo, we're hoping in the range of 80 to 115 megaparsecs. And CAGRA, they're going to start out down at the 1 megaparsec level, but try to improve through a sequence of commissioning breaks over the run to come back towards the end of the run, targeting hopefully to get to around 10 megaparsecs. The one other thing to mention here is that our baseline is a year for this. We all, I think, understand that there are constraints in the gap between 04 and 05 that require us to have enough time to do installation work and commissioning work to upgrade the detectors for 05, that we're striking a balance. There's some interest from some astrophysicists and astronomers that the run might go longer, but I think it's right now we're at a year. That's the baseline. We'll have some discussions with others to figure out if we want to extend or not. I can't remember what my next slide is, so let me just go for a, okay. Let me just go through this. This is very fast. I gave this to a theorist audience, and so I only did one slide to give them a sense of the types of work that is being done on the detectors. So I've added a little extra here that this is 2 slides summarizing what's going on in LIGO. If you want to see a little more detail of that, I encourage you to go to the webinar that's linked here. You can find that by going to LIGO or the EGO or the Virgo websites and actually looking for the link to the last webinar. There are lots of details about LIGO, Virgo, and CAGRA's work between 03 and 04 in that presentation. Anyway, for LIGO, the upgrades that we've had ongoing is to change out the laser amplifier, deal with the point absorbers on the test masses, add in frequency-dependent squeezing, which was a major step because it had construction work requirements, improve adaptive mode matching, add and bring in the low-loss Faraday isolators, and also to increase the baffling within the detector. And so the list of the impacts, this audience could probably just guess at all of those for the most part, but the list of impacts here are given to me by Peter Fritschel to understand exactly what could go on. Nevertheless, the outcome of all of this is that after that upgrade and commissioning, we hope to come back with a range in binary neutron star range as high as 190 megaparsecs. That would be almost a factor of 2 improvement over 03. And a factor of 2 would be a factor of 8 in rate. And so that's the best, I think, that we could hope for. Probably it's more likely it'll come in at about 1.6. And so you'll see something like 160 megaparsecs. And that will be somewhere around between 1.5 and 1.6 in rate. Sorry, let me rephrase that. That will be 1.5 or 1.6 in amplitude, which will get us up to around 3 to 5 in rate, depending on how it goes. The requisite photos of how things have been going. This was the construction of the filter cavity at the site. Thankfully, the construction work is finished at LIGO, at Livingston, and at Hanford. There was also a new outreach center built at Hanford. They're going to have the opening ceremony for that on the 2nd of June. So they're actually ready to go with that as well. So this is all good news. No more heavy construction on site in preparation for 04. Again, some of the equipment that has been modified and some pictures of the people doing the work on it. I'm not going to do much on that. You can take a quick look, see if you can identify anybody. We're all used to spotting people in masks these days, so you never know. And yeah, so what is the impact of all of this on our observations? So this is the thing that then I want to turn to. So for 04, I think the thing to do is take what I was saying about the improvements in the rate in sensitivity and think about its impact on our detection rate. So the first thing is we had a detection every 5 days, approximately in 03. With the 04 target sensitivities, we can anticipate a detection every 1 to 2 days if we really do well. That's a big jump in the detection rate. And for our collaborations, that's going to be a big change in how we can deal with those detections and make sure we extract maximum science in a timely way. But on top of that, with the improved sensitivities and from LIGO and Virgo, we're going to get better localization of the sources. We'll get better classification due to the SNRs being better. We'll get lower latency due to improvements in our infrastructure. And so all of those are critical for us as we move forward to the next sort of phase of our science, observational science mission. So on the right, I have, this is also one of those things that catches everyone's attention because it sort of somehow feels like a wonderful thing to be able to measure a gravitational wave. And then rather than waiting until after some collision happens, you, in advance of the collision, point at the sky and say, hey, there's a pair of neutron stars going to collide over there in X seconds. So we refer to it as early warning. It feels quite wonderful. I mean, it's not very often that we get to look up at the sky and say, well, okay, you know that star over there, it's going to go supernova next year. Let's keep looking, right? So this is really wonderful in this regard. But we need a lot of signal to noise ratio to do it well, and we would need our low frequency sensitivities to be very good to do it well. Nevertheless, if you take a look at this estimate by Ryan McGee et al. From last year, you'll see on the horizontal axis, this is the time before coalescence, going from 1/10 of a second, 1 second, 10 seconds, 100 seconds. And then this is a cumulative histogram of the expected number of candidates of neutron star detections that you would have. The upper one is really what I think is more realistic. The lower one was based on sort of a slightly more restrictive estimate on the rates. Nevertheless, what you really see here when you start to look at it is you could hope for a few, that you detect at merger essentially. And that's what we'd expect because we've detected a couple of binary neutron stars so far. You get an increase in the rate of order, say 3 to 5. And so we should be somewhere up around 6 to 10, depending on exactly what happens. And then if you go to 1 second, you might have a few that you could get at 1 second, but when you get to 10 seconds or 100 seconds, we can't actually say much. So I consider this to be the kind of optimistic scenario of order 1 to 2, where the early warning could be about 10 seconds during 04. Very, very contingent on the low frequency noise, but still it would be a huge milestone. So what else? Let me skip that. I want to skip those things. So what else? So the thing that I want to do now is I want to come back to what we're going to try and do for 05. I've skipped over the sensitivity curve projections there, but I want to talk about the run itself. So we've got a very tentative plan that starts us running sometime in late 2026 and runs on through to 2028 or thereabouts. Right now, there's a sort of a tentative plan from LIGO that might turn on a little earlier with commissioning breaks, balancing the ability to stabilize the instruments for observations and then do improvements and go again. Whether that stands the test of time is unclear to me, but what I think we should take away from this is that the first thing is our targets in sensitivity are quite substantial. We're going to 325 megaparsecs at the upper end for the LIGO detectors towards the end of 05. We're going to 260 megaparsecs at the high end for Virgo come 05, and perhaps having Kagra at around 130. That means that we are going to increase the rate over 03, okay, by somewhere like a factor of 20 to 30. And so what you go from is the 1 per 5 day detections of compact binaries to having about 3 detections per day of compact binaries. You also move into an era where you've got multi-year runs. And so everything looks different for 05. I mean, the rates are so much higher, and the duration of the run just means that everything changes about how you do your data analysis. The improved SNRs are also a great thing. This is one of our results of the upper limits on the strength of gravitational waves on the vertical axis versus frequency for continuous wave sources. So things like a single isolated neutron star spinning at, somewhere in the kilohertz type region within our galaxy, then these are the upper limits on the gravitational wave stream. We all know that we've been able to constrain for some of the known pulsars the gravitational wave ellipticity to down below sort of typical upper limit expectations. So we're beginning to dig in for some of the pulsars below the estimates for the upper end of their gravitational wave ellipticity. So as a result, I really like to look to CW, to be honest, as the next discovery space. Every time we get an increase in sensitivity of order a factor of 2, that's going to really push our ability to do things. And so we really need to be thinking about the possibility of seeing, as the sensitivity clicks up, of seeing a signal and then being able to decide we want to publish it. This graphic is always a little tricky to interpret, but I want to just sort of give the sort of core message. This was a simulation that Matt Pitkin et al. Did back in 2018 and reported it. The basic idea was, what do you think are the number of pulsars and continuous wave signals that you might detect at a given set of sensitivities of LIGO and Virgo instruments? And so in this plot, this one is actually a graph for 2 advanced LIGO plus detectors, so 2 A plus detectors, and the advanced Virgo detector. It doesn't push into advanced Virgo plus. The solid boxes down here are the estimates of the number of events with a given SNR for just the initial, for the advanced LIGO turning on basically in 2015 plus advanced Virgo. Okay. When you though crank up the sensitivities like this, you begin to see a few events or a few objects trickling in with signal to noise ratios above 10 certainly, and then in the 5 to 10 range. And of course, this is just one set of simulations and one instance of what might be the case in the universe, but it tells you that we could have something out there that as we break through to get to these sensitivities, we'll actually reach signal to noise ratios like this for a few objects that happen to be nearby and well-oriented. So with that, then, the other thing we can look at is the stochastic background. And we've got our upper limits on the amount of gravitational wave background that exists. This is a graphic that shows that across the sky, where the color code just tells you what the upper limit is. But when we look then to the future, we begin to sort of ask the question, well, what might we be able to do with our stochastic and gravitational wave background analysis? And this diagram again shows the frequency along the horizontal axis from 10 to 1000 hertz, and then the energy in the gravitational wave background on the vertical axis. These curves represent different sensitivity limits. You can look at the legend down below. And in particular, if you take a look here at this dot dash limit that's going in here, you see that that's just the design A plus level. The design Hanford Livingston Virgo one is sitting in here. And so if you take a look at that and you compare it to binary neutron star gravitational wave background, so from collision of binary neutron stars and from binary black holes, then this is the curve that we think would be the spectrum coming in the gravitational wave background from those objects. And so you begin to see that we start to creep in there and might be able to make detections as we get to these design sensitivities for these instruments. So again, being still the background from the collision of binary black holes and binary neutron stars, it may not be as exciting as getting at the cosmological background, but it still will allow us to start to probe a set of questions that we can't do with the other sources. Okay, so this one, I'll skip over this slide rather quickly, but this was actually a message for the astronomy community. And that is to say that with the detectors so far, we've emphasized 04 and 05 and talked about run plans through roughly the 2020s, but LIGO, Virgo, and Kagra are all committed to running their instruments in observation mode beyond 2028. Everything is contingent on funding, but the point about it is that with an investment in the detectors like we've made already, it would be rather disappointing and might even say foolish to set them aside at some point and not run them. So there's a lot of work ongoing on speccing out what we might be able to do by way of sensitivity improvements for each of the detectors, taking account of the limits from the facilities in which the detectors are housed. And I noted a couple of things about what LIGO is exploring in terms of the pathways and things. Well, let me just say, if you think about it, there's two sort of major approaches you could take. One is you could do a major upgrade. So you'd be offline with at least one of the detectors for a long period of time. So you might go for something like LIGO Voyager, going all the way to cryogenic. Or you could go a path of more incremental upgrades. And the actual final decision is still to be made, but it's a trade-off in where you go. In the end, the truth is we also need to keep an eye on the other end of this, and which is the third generation detectors. And we need to take a look at a way where the current generation of detectors and their observational capabilities dovetail with the new third generations as they come online. So with that, I'm going to finish with just a brief reminder. I don't have to remind any of you about Einstein telescope. You're well aware of it. So there's the beautiful picture of it underground. It's exciting. It was very exciting to see it go on the S3 roadmap back in 2021. That was a major milestone. And it's been very interesting to read the various news articles about which countries are investing in it. So I'm very excited and impressed. I'm going to switch gears to Cosmic Explorer for a moment, because that effort is behind Einstein Telescope in terms of how well developed the plan is. This is a US-centered concept for an above ground facility. It is the baselines that are being discussed in this Cosmic Explorer Horizon study that you may have already seen, but if you haven't, it's worth a read. It's short enough to do a quick skim of. The baselines are to go to 20 or 40 kilometers. So that's scaling up the detectors by basically an order of magnitude. And the thing about this horizon study is there's been a number of workshops and a number of white papers written to get the message out to the community in North America, and in particular in the US. And at the last workshop, the Dawn workshop, there was a statement in the final report that actually endorsed the Cosmic Explorer Horizon study. And that sets the path for them to begin a design phase, and then to eventually go to develop a proposal and so forth. It's a long road, but still, as of today, that the roadmap still shows mid-2030s as operating with those detectors. I'm going to end with this slide here because, again, I've found it a nice way to visualize the trade-offs that were being made. And I thought I think it's worth, it really is worth sort of looking at it, and it provides a very simple registration of those trade-offs. On the left is a diagram that's meant to be essentially a cartoon that shows a sense of the sensitivities of each of the different types of detectors, and I'll go through those in a moment. It also shows as dots here on the left a population of binary neutron star mergers in the universe. And so where they're most dense, that's the distance out in the universe where the majority of them will happen. And in the tails, then you have nearby ones being rare, but also very distant ones being rare. Similarly, the white dots, they represent binary black hole collisions. And again, the same peak in the distribution and the outside. So now, if you take a look at the color coding, and we may as well focus on the right-hand side here first. There's a ring here, which is a little tricky to see, but it's the O3 ring. This is the sensitivity reaching out, imagining the detectors at the middle, that the distance out to the ring represents the sensitivity or the range to which we can see objects. And that's the sensitivity of the O3 network. Okay, so we were probing the sort of initial tail of the binary black hole merger distribution. If you take a look at this blue line, this is the advanced LIGO plus, so the A plus design curve and sensitivity curve, and you start to get right into the heart of that distribution of binary black hole mergers. So it's actually pretty good. When you get to, if you try Voyager out, you can sort of pull in the majority of these things. At least you get over the peak of the mass function for them, or pardon me, of the distance function for them. And so you start to be able to see a lot of them and be able to resolve certain redshift structure if you had a Voyager detector. But if you look then at Cosmic Explorer and the ET right out here for these 3030 solar mass collisions, you see that they really are probing way out into the high redshift universe. And the story basically goes, we can see every black hole, binary black hole merger that happens while the detectors are operating. And that's a pretty amazing thing. That translates, by the way, with our rate estimates into one every about 5 minutes, which is quite a nice event rate. So that's the sensitivity on the right for the binary black holes. On the left is for the neutron stars, and I think this is where also things are much more telling. You see our O3 sensitivity is right in, and we only have a very small number of things we have access to. We will do better with as we get to O5. Voyager would begin to see stuff in that regime, but to really be able to probe the peak of that distribution as a function of redshift, you really do need to go to ET and Cosmic Explorer. There's no way you can do it otherwise. And so over on the right, this representation is a representation of the trade studies between building, say, 20-kilometer detector, a 40-kilometer, a pair of 20s, and so on. The darker the color, the better the science you can do on a particular thing. So they list a number of themes with a number of science goals down the left. I won't go through them, but what you can see, of course, is that as you go to a place whereby you increase the number of detectors, you always tend to do better. So CE, Cosmic Explorer with ET, tends to do pretty well if you can get a pair of Cosmic Explorers. Cosmic Explorer with ET and a Cosmic Explorer in the Southern Hemisphere really does very well. And so, again, being able to represent sort of, first of all, a set of science goals, and then how well you can do is actually very, very nice on this diagram. So with that, I'm going to end, and thank you for your attention.
Yeah, you've been talking of the evolution of, say, the way we approach to data, while the number of events will keep increasing. So I was wondering what will happen on the modality we do that analysis. So now we make, for instance, accurate parameter estimation for each single event. When we start having a few events per day, how will this work?
Yeah. So I think that's a great question, and one we need an answer to. We don't really have one, I think. I think the first thing is I think we will emphasize the higher quality events. So the ones that we're very sure are astrophysical. So that'll limit the number we process, but it's still going to be a large number. And the thing that I think, I guess, let me highlight the thing that I worry the most about in this. Right now, our parameter estimation takes a long time. And the reason really is that we use Markov chain Monte Carlo approaches to probe the distribution function across the parameter space. They're highly serialized and they need to be tuned. There's just no way around. They require babysitting, and that causes delays. So I think the challenge for us there is, how do we build, probably still using MCMC or other tools, how do we build a set of tools that can robustly run in what I think of as wide, so they can have many processors contributing to trying to get the parameters for a single event, and where we don't have to babysit the analysis, because that's the real thing that hurts us in it. If it's automated, I think we can get the computing resources, especially if we take advantage of increased density and so forth. And I think we can process most of the events, at least, that we will see with Virgo and LIGO and Kagra as time goes on. What happens with next generation? Well, that's a different problem. But yeah, so.
Yeah, thank you, Patrick. Can you come back to the drawing with the, yes, that one? I wanted just to notice how lucky we've been with the two black holes and the two neutron stars. This graph here really tells you that we have been extremely lucky, especially for the neutron stars.
Yeah, there's a little thing that's a little misleading about this graph, in the following sense, that, and I actually agree, it still shows you how lucky it is, especially with the neutron star case, because, I mean, let's face it, it looks like it's on top of the detector. But the graph is maybe a little misleading for starting to be for 150914, because they chose just a density of the dots in order to be able to have some sense of different densities across the whole range. And it may not be truly representative of the absolute number per unit observation time or something when you try to count up the dots right now. So, yeah.
But about luck, the astronomers tell us that when you turn on a new instrument, first thing that you do is a new discovery. So we just respected the rule, and we hope to make again at the next run.
Yep.
I would like to ask a difficult question, which I always ask myself, and I don't have an answer. So we have started multi-messenger observations, been a breakthrough. But O3 has shown that we are doing most of the science on the basis of gravitational wave data only.
Yep.
And the further we look, so the more sensitive we get, the more difficult it gets for the telescope to be able to follow up the observations.
Yep.
So the question is about strategy. How can we really manage, let's say, the pressure from the astronomers who want, let's say, this service of alerts for pointing the telescope, with the evidence that so far multi-messenger is only a small part of the science we are providing?
Yeah, you know, it is I like the way you're asking the question, and it's good to keep asking it, because I think it's a real. I think we sort of, there's too much emphasis on MMA in a sense right now. I mean, that's the fact. We know that we've had one counterpart, which was nearly on top of us, that we detected. We've had one more BNS and a couple of NSBHs in the last run. So we know how many of these things we're going to get in each run. And then I start to do the math as follows. I say, well, suppose I go into run and I have n of those objects that are going to be detected in gravitational waves. Let's make n 10 for a moment. So that maybe is a ballpark for 04 for binary neutron stars. So the first thing is that half of them are in daylight. Okay, so that's the very first thing. So now you're down to 5. And then, and by the way, it's not quite half, but still, I'm going to be dramatic in my conversation. So you're down to 5, right? The second thing is that they're going to be northern and southern hemisphere, and you don't have the same sensitivities with telescopes in those two hemispheres. So you're going to lose a little bit there. It's not the same, not another factor of 2, but it's maybe 20%. So now you're down to 3. So the thing you start to see when you start to do it, and this is very naive, right? This is not a careful calculation, but when you start doing it, you start to see that the ability to actually detect a counterpart for one of these objects is quite low until you get the rate much higher. So I think that's the key. And we didn't know enough about the neutron star binary rates before to be sure about where it would go. But we now do, or at least we can say more. And so I think now we sort of can do better estimates of that. And I think the truth is that in the number of detections and the measurements we're going to make, it's going to be, most of the science will come from the gravitational waves. But of course, that means that the few that we get in multi-messenger are going to bring a lot because they're going to be rare. And I think when you start to then look at the balancing act of having to send out alerts carefully and other things, it's still worth it. It just isn't, it isn't the dog, it's just the tail. So, yeah.
If they attend, the possibility that at least one is pointing to us.
Yeah.
It
yes,
is,
it's another
then if you get something bang on, probably there you get another of your milestones there.
Absolutely. And I think that's the key. The key here is that it is a great discovery space, and it's going to be exciting because the fact that we're bringing together data of different modalities into the same observation is exciting because it just shows us more about the objects. But it'll be a few events. It won't be a huge plethora of them. So, yeah.
Very good. Any other question before we go to the... Also for remote, yes, but I did not, unfortunately, were there any questions in remote? I didn't, unfortunately, I did not connect. But they can open, yes, please open and speak. Huh? It's open, so they're all, I have one very fast question. When do you think, because it is difficult, we know, coming in, LIGO India, when do you believe that they could be able to join finally and to be at some decent?
It's a very difficult question. We know that the project has been with their prime minister's office for a number of years now. The pandemic and now the outfall from that is going to cause more tensions on whether or not they can, what they do. I think so certainly the LIGO laboratory team that interfaces with the LIGO India group continue to make progress on what they can, but it's fundamentally answering the question is impossible without knowing that the funds have been released. And so it really just depends on that. And so, yeah,
okay.
Let me not say more.
So I think, thank you again, Patrick. It was really very interesting.